In this video, we will introduce our final project, colorizing black-white movies fastly and automatically. The group members are Chen Yanglei, 亚洲行, Yue Wu, and Jiaxin Xie. Colorization aims at converting black-white images to natural color images. Most related works focus on image colorization, and their objective is to generate visually natural images. Our task is to colorize a grayscale video. This requires temporal coherence. Besides that, every single frame should be colorized naturally. Moreover, the process should also be efficient, since video input is much larger than image input. Earlier movies are all black and white due to the limitation of film technology at that time. Using our method, colorizing black and white movies efficiently becomes possible. This is the framework of Zhang's work, which does single image colorization. Each convolutional layer refers to a block of 2 or 3 repeated convolutional and ReLU layers, followed by a batch normalization layer. They use a very simple network structure to estimate the probability of color. This figure shows the framework of Lizuka's work. Their model consists of 4 main components: a low-level features network, a middle-level features network, a global features network, and a colorization network. This figure shows the framework of our method. Given a sequence of grayscale video frames G, our objective is to colorize the given frames as realistic as possible automatically. The illustration of symbols is as follows. G is the input grayscale frame. C represents the colorized result generated by our network. The backbone of our method is a U-net network structure. Given 2 consecutive frames, GT and GT plus 1, fit them into 2 different U-net, then compute the loss between 2 consecutive output colorized results, CT and CT plus 1. For the video colorization problem, it is quite essential to make the result temporal coherent and diverse. Thus, in our model, we have 2 loss functions. The first is a temporal loss to regularize the temporal consistency. LT equals to the second norm between warped normal C2 and ground truth C2. W is the warp operator to warp frame C1 to frame C2 using optic flow 2 to 1. The second is a diversity loss that aims at producing a diverse set of colorized videos. Y represents the corresponding RGB color image ground truth. Phi represents the function to calculate perceptual loss. LD is the sum of the minimal perceptual loss distance and the weighted sum of all the perceptual loss distance. In experiment, we adopt the Davis dataset to evaluate the performance. The test set consists of 30 videos. Each video has 30 to 100 frames. We convert them to gray frames as input and use the RGB result as ground truth. The following 3 images are examples from the Davis dataset. We choose 2 single image colorization methods, Zhang's work and Lizuka's work, which we also introduce in related work, and another single image method, Lei's work, as baseline. From Table 1, we find that our performance outperforms 2 single image baseline on PSNR and achieves similar performance compared with Lei's method. However, Our method is much faster than this method because we do not need to compute the optical flow and refine the result again on the test stage. This figure shows the comparisons between our method and the single image method. These two rows are the input and the results for two consecutive frames. We could see that the colorization of our method is much more stable than single image method. Single image colorization method gets inconsistent colorization results because they are trained without considering the temporal coherence. In this project, we propose a CNN model to do video colorization. Through modification of our baseline model, we speed up the network forward time by 30% while still keep the comparable accuracy. Also, our model gets rid of hard-to-obtain optical flow during testing. Compared with state-of-the-art image colorization works, our results keep temporal coherence and multimodality.